We're going to keep going with interference, but we're going to expand it a little bit. Standing waves are not the only kind of interference we see, so we need a way to discuss interference in more general terms, and we're going to use that. We're going to develop a method that discusses interference using phase difference. So we started phase difference at the end of chapter 16. If you're a little bit shaky on it, you might want to go back and review. It'll probably only take you a few minutes. Because we're going to build on what we did at the end of chapter 16 now to discuss phase difference and how it applies to interference in all of our general situations. So let's start with our setup. We have two sources of waves. So if you're thinking about a source of a wave, it might be speakers with sound waves, or it could be flashlights with light waves. So we have two sources, and they're emitting waves that have the same frequency and the same wavelength, and it's happening at the same time. Our two sources are going to be pretty much on top of each other or in a line. So if this is source number one, I'm drawing a speaker just because I can draw speakers. Source number one emits a wave and it comes out, whatever it looks like. Source number two is not at exactly the same position as source number one. Let's put it a little bit behind. And it's also emitting a wave. These waves are a little bit hard for me to draw freehand. So let's say that this one emits a wave that looks kind of like this. Okay, so it looks like a little bit of a mess, but we have two sources. They're each emitting a wave, and the waves have the same frequency and the same wavelength, and it's happening at the same time. So there's our setup. In the pictures I draw from now on, and the pictures I use, I won't put them on top of each other just because it's a little hard to get all the labeling in there. I'll separate them vertically a little bit just so they're easier to see. But imagine that they are all in a line that way. So the first thing we'd like to establish if we're talking about phase difference is how do we write down what phase difference is. So if I were going to describe the height of wave 1 as a function of time, I would write down the equation of motion for wave 1. So that equation of motion would be d1, so the height of this wave, is equal to the amplitude times the sine of the wave number k, which is 2 pi over lambda, times x1. x1 refers to the distance between the source and the point I'm looking at. Okay, so that part is pretty important. So x1 is the distance between the source and the point you care about. I'm going to assume my waves are traveling right. You could also apply this description to leftward traveling waves. So kx1 minus omega t, omega is 2 pi times the frequency, plus the phase constant delta phi naught. Normally I just write delta phi naught. Since this is for wave 1, I'm going to say delta phi naught 1. So x1 is from source to the point where you're measuring the height of the wave. So I'll say from source to point. So this part right here, this is the phase of wave 1. And d1 is the height of wave 1 that has amplitude A, wavelength lambda, frequency f at position x1 at time t. I can do a similar sort of thing for wave number 2. I can write down the equation of motion for wave 2. So wave 2 has a height of the amplitude. I'm going to assume that my waves have the same amplitude. They don't have to, but let's start with things easier rather than harder. Times the sine of k times x2. x2 here is the distance from source 2 to the point where we're measuring the height of the wave, minus omega t plus phi naught 2. This then is the phase of wave 2, phi 2. So careful here, phi naught means phase constant. It's the way the wave starts off. Is it at a crest, a trough, an equilibrium, somewhere in between? So phi naught tells us the starting point. Phi, the phase, tells us everything. So where, when, and how did it start? x2 is from source 2 to the point. So where we're going to look, what we're going to use to describe interference is going to be the phase difference. The phase difference, and that's here. How do we write the phase difference? The phase difference is the difference in phase. So delta phi is the phase difference. It is exactly what it sounds like. It's the difference between these two things. So it's phase 2, take away phase 1. So let's fill in our phase 2. Kx2 minus omega t plus phi naught 2 subtract kx1 minus omega t plus phi naught 1. So I just straight up put in my phi 1 and phi 2. I've got k outside of x2 minus k x1, so x2 minus x1, minus omega t minus omega t gives us plus omega t, plus phi naught 2 minus phi naught 1. Okay, let's look at each one of these terms, and are they telling us something that we can do? Well, let's remember that k is our wave number. Wave number is 2 pi over lambda wavelength, and they both have the same wavelengths. x2 minus x1, we can label that as delta x. Delta x is pretty important, and this is a place where people get astray all the time. Delta x is called the path difference. Okay, so delta phi is the phase difference. Delta x is the path difference. It means how much further away from the point is this source compared to this source. So it's the difference between these two distances. That's where people get tangled up the most often in these problems, so be careful you're straight with your delta x. The path difference is how much further away is one than the other. It doesn't matter which one is bigger, so normally we say that delta x is the absolute value of x2 minus x1. Okay, so it's just the difference in them. It doesn't matter which is bigger. Minus omega t plus omega t, that's going to give us 0. Plus phi naught 2 minus phi naught 1, that's delta phi naught. And then delta phi naught would be the difference between how these waves start. If they both started at the same point, this would be 0. If they started at different points in the cycle, then it wouldn't be 0. We're going to look at some special cases. Okay, so now let's put all this together and we'll write down our expression for phase difference. So delta phi, the phase difference is 2 pi over lambda times delta x plus delta phi naught. This is the phase difference at some point p between any two waves that have the same amplitude, wavelength, and frequency. Okay, so that's phase difference. Now let's start building to interference. When we talked about interference, we talked about constructive and destructive, so let's talk about constructive and destructive again. So if we want to remember what constructive and destructive interference are, let's start with constructive. What does constructive mean? Constructive means waves meet up either both on a crest or both on a trough. So constructive interference is what happens when two waves meet up at the same point in their cycle. So for these two waves, I've drawn my point P right here. So here is point P. Here is point P. Remember, these waves are really on top of each other, but that's just a bit hard to draw. If we ask what kind of interference happens at this dashed line, we see that the waves meet crest to crest. If the waves meet crest to crest, we know that that's constructive interference. Here's the part you need to remember from what we talked about in chapter 16. What's the condition for phase difference to get constructive interference? Well, we know that any time we get constructive interference, the phase difference delta pi, it could be 0, it could be 2 pi, could be 4 pi, could be 6 pi, any of those numbers. In general, we write that as m times 2 pi, where m is our integers, 0, 1, 2, and 3. So this is our condition for constructive interference. It happens whenever the phase difference is an even multiple of 2 pi. And that makes sense. So we get constructive interference whenever they meet up at the same point in the cycle. So crest to crest, trough to trough, equilibrium to equilibrium. So that's where we get constructive interference. Let's apply constructive interference to our equation for phase difference and see what does that tell us about delta x. So if we have constructive interference, then 2 pi over lambda times delta x plus delta phi naught equals m times 2 pi, where m is equal to 0, 1, 2, and so on. So if we wanted to find, for example, our wavelength and we knew delta x and delta phi naught, we could solve for our wavelength. So that's how we get constructive, and we're going to apply some special conditions to this delta phi naught, but let's talk about destructive interference first. So crest to crest, constructive, which is m times 2 pi, and we apply that to our equation for phase difference. So if this is m times 2 pi, then we have constructive interference. Okay, let's do destructive, and then we'll do some special cases. The other kind of interference we talked about was when two waves come together and they cancel. So in this picture, our point P is here, point P is here. These two waves meet crest to trough. Whenever two waves meet crest to trough, or at completely opposite points in their cycle, that's destructive interference. The way we write down destructive interference is we know that the phase difference has to be pi, or 3 pi, or 5 pi, and so on, and we discussed that in chapter 16. So if your phase difference is pi, 3 pi, 5 pi, those numbers, then we have destructive interference. The way we write this guy down is we say m plus 1/2 times 2 pi, where m is equal to 0, 1, 2, and so on. So we get destructive whenever they're off by a half cycle. So a full cycle will get them lining up crest to crest, like this. A half cycle gets them lining up crest to trough. So let's apply our condition for destructive interference to our equation for phase difference, and then we'll have that general relationship. So our phase difference is 2 pi over lambda times delta x plus delta phi naught. If we have destructive interference, then it's m plus 1/2 times 2 pi, where m equals 0, 1, 2, and so on. Okay, so far we've talked about how do we find phase difference. We've got our expression for phase difference. We talked about how do we know if it's constructive or destructive. Whenever they meet crest to crest and delta phi is a multiple of 2 pi, then it's constructive. Whenever they meet crest to trough and it's an odd multiple of pi, then it's destructive. Okay, next thing we'll talk about is this phase difference, or the difference in phase constant, so delta phi naught between waves 1 and 2. So I've got two pictures on the same one. And let's ask what happens when the two sources emit waves in phase. So we need to ask, what do we mean by emitting in phase? In phase means that the two waves come out in the same point in the cycle. So for example, when our two speakers emit sound, they might both emit on a crest, or they might both emit on a trough, or they might both emit at an equilibrium and then go upwards. So in phase means in the same point of the cycle. And for an example, they might both emit on a crest. Or they might both emit on a trough. So how do we apply this to what we have? So if they both emit at the same point in the cycle, then delta phi naught equals 0 because they emit beginning at the same way, because they start in phase. Okay, so they're exactly lined up. They're at exactly the same point. If delta phi naught is equal to 0, let's put that into our condition for constructive interference. So 2 pi over lambda times delta x equals m times 2 pi. We've got 2 pi on either side, so we could divide both sides by 2 pi. And we get that delta x equals m times lambda, where m equals 0, 1, 2, and so on. So if we have two sources emitting sound in phase, and we have constructive interference, then the path difference must be an integer multiple of the wavelength. And that makes sense. If we meet up, if they're off by exactly one wavelength, then they'll always meet up crest to crest or crest to trough. So this, why don't we even put in a reminder here that delta x is the path difference. And that's how much further away is this source compared to this source. So that's how we get constructive when they start in phase. Let's go the same deal, but destructive. So these, in our picture here, we've still got two sources. They emit in the same way. So delta phi naught equals 0. I probably don't have to write it down again, but it'll look nicer if I do. So they're in phase. So let's put delta phi equals 0 in this equation. We get 2 pi over lambda times delta x plus 0 equals m plus 1/2 times 2 pi, where m is 0, 1, 2, 3, and so on. Our 2 pi's cancel. We divide both sides by 2 pi. And our path difference, delta x, then, is m plus 1/2 times lambda. So if our path difference, is off by 1/2 of a wavelength, then we'll get destructive interference. Okay, so that says if we have two sources in phase, if they emit the same way, then we get constructive interference whenever our path difference is an integer multiple of lambda, and we get destructive interference whenever our path difference is a 1/2 multiple of lambda. So the next and last thing to discuss, special conditions, is what happens if they don't emit the same way. What if they emit opposite ways? And if they emit opposite ways, that's called out of phase. So what happens when our two sources emit waves out of phase in opposite ways? So what we could mean by that, for example, one emits on a crest, and other emits on trough. For example. So our conditions for phase difference are the same. We get constructive if your phase difference is a multiple of 2 pi. We get destructive if your phase difference is a 1/2 multiple of 2 pi. Let's see what happens if our delta phi corresponds with out of phase. So the first thing we'll deal with is, what is delta phi if your phase difference is out of phase? Oh, hang on, I think I said something wrong there. What is delta phi naught if the two waves are out of phase? There, I definitely said that one right. So out of phase means they're off by a 1/2 cycle. if they're different by a half cycle, then delta phi naught, we've got two choices. One wave can be pi radians ahead, or it can be pi radians behind. So delta phi naught is going to be plus or minus pi. Both are acceptable, so delta phi equals plus pi and delta phi equals minus pi gives us exactly the same behavior. It tells us that this source can be a half cycle ahead or a half cycle behind. And it doesn't matter if it's a half cycle ahead or behind because the mathematical treatment is still the same. So let's put this delta phi naught into our equation and see what do we get for our conditions for wavelength then. So let's start with constructive. So I can have plus or minus phi. In this case for constructive, I'm going to use minus pi. Okay, and I'm going to justify that afterwards. They're both legitimate. They will both give the right answer. Let's work through it and see what we get when we use minus pi. So our phase difference delta phi is 2 pi over lambda times delta x minus pi equals m times 2 pi. Let's get delta x. Let's try and get delta x on one side, everything else on the other side. So I'll bring my 2 pi to the other side. 2 pi over lambda times delta x equals m times 2 pi plus pi. I've got a 2 pi here, a 2 pi here. How do I get a 2 pi here? Well, I can multiply and divide by 2 pi. So then what I get is that those 2 pi's we can divide through. So then that tells me that delta x over lambda equals m plus 1/2, or delta x equals m plus 1/2 times lambda, where m equals 0, 1, 2, and so on. So this is why I picked minus pi, since both were legitimate. If I had picked plus pi here, I would have had minus here, minus here, minus here, and my conditions for m would have been different. I would have had to start for 1. I wanted my values of m to always be 0, 1, 2, 3, so I chose minus pi here. So let's do the destructive, and then we'll see what we notice when we compare in-phase waves to out-of-phase waves. Okay, so destructive next. For destructive, delta phi naught is either plus pi or minus pi. This time I'm going to use plus pi. If I use plus pi, then I have 2 pi over lambda times delta x plus pi equals m plus 1/2 times 2 pi. I'm going to multiply that 2 pi through, so I have m times 2 pi plus 1/2 times 2 pi, or pi. So I've got a pi here and a pi here. I can subtract pi on both sides, which leaves me with 2 pi over lambda times delta x equals m times 2 pi. Now what we see is we can divide both sides by 2 pi, and we're left with delta x equals m times lambda, where m equals 1, 0, 1, 2, and so on. And again, just like before, delta x is your path difference. So this looks like what we did before with the in phase, but it's not exactly the same. If the two waves were in phase, our conditions for delta phi are the same. Okay? So our phase difference is always constructive as a multiple of 2 pi. Destructive is always a half multiple of 2 pi. But if they start in phase, then we can put in our values for our initial phase constants, and we see that the wavelength is an integer multiple of lambda to get constructive, and it's a half multiple of lambda to get destructive. That's because they start at the same point, right? So they have to go either the same number of wavelengths for constructive or different by a half wavelength for destructive. If they start in opposite ways, then to get to constructive, they have to go a distance that's different by a half wavelength, so it catches up. If they start out of phase and they go the same number of wavelengths, then they'll end up at a phase and it'll be destructive. So as you go through these problems, make sure you're really careful of, are they in phase or out of phase, and how do we get constructive and how do we get destructive? Make sure you don't get those mixed up. And of course, you can have conditions where this delta phi naught is not exactly in phase or out of phase. That can happen too, and we may look at a couple of examples there.